everyone. Welcome to the 9th UQM virtual seminar. Today we are happy to have Arpit Dua and Islam Khalaf as our speakers who will be talking about their latest research. So our first speaker is Arpit Dua, and he's gonna tell us about structure of Fracton stabilizer models. Arpit, take it away.
Hi, everyone. Yes, my talk is on structure of Fracton stabilizer models. So first I would introduce topological stabilizer models and then talk about the entanglement renormalization of these models. And then I will discuss polynomial representation for translation invariant stabilizer models. And then I would prove a structure theorem for 3D bosonic particle, by which I mean that if there exists a bosonic particle which is mobile in all 3 dimensions, then you can do a local unitary to extract a 3D toric code from that stabilizer model. So yes. So I want to start with a very basic introduction to topological order. So topologically ordered phases are gapped quantum phases, which are equivalence classes of ground state wave functions, which go beyond the conventional paradigm of symmetry breaking. And they're described by locally indistinguishable ground states that cannot be created by a constant depth local circuit. And there's a so-called topological order, which is described by topological quantum field theories. And in such order, you have a purely topology dependent ground state degeneracy. And you have quasi-particle excitations that can move around freely. So there's a whole class of gapped quantum phases which are stable in the sense that their ground state degeneracy is stable to perturbations, to local perturbations. And these stable gapped quantum phases are further divided into non-liquids and liquids. And liquids are such phases in which when you go to the long wavelength limit, the geometry of the lattice is not important, or geometrical features are not important in the long range limit. These are described by topological quantum field theories. And on the other side, there are non-liquid phases, in which case the lattice geometry remains an important feature even in the IR. And Fracton topological order falls under the non-liquid side. And if you go further in these, on the two sides, you have Fracton stabilizer models and TQFT stabilizer models. So we are going to be focusing on these stabilizer models. We will focus on stabilizer models which are topological, made out of qubits, and which are translation invariant. And they are described by Hamiltonians with commuting polyterms. Each term is called a stabilizer term, and it is a tensor product of polyoperators X and Z acting locally on a set of qubits. And the operators that map between different ground states are called as logical operators. The famous example is the Toric code, which has a star operator that is made out of X polyoperators and a Plechet operator made out of Z polyoperator. And this has a TQFT topological order. And the Hamiltonian is a sum of these terms. So I want to summarize the types of Fracton topological order. So besides the Fracton side, we talked about TQFT. And the example for this is the 3D toric code or the 2D toric code, for example. And in this case, the string operators are deformable in 3 dimensions for a 3D TQFT stabilizer model. By string operators, I mean here the operators which move excitations apart along the line. And the ground state degeneracy in this case is constant with system size. And then there's a type 1 Fracton order, for which famous example is the X-cube model. These type 1 models are characterized by lower dimensional excitations, which means the excitations are mobile in submanifolds of the 3-dimensional model. And the string operators are rigid. And these are characterized by sub-extensive ground space degeneracy. They are further classified into foliated type 1 and fractal type 1. And foliated type 1 have a foliated structure, which I will describe briefly. And fractal type 1 are characterized by fractal logical operators. And for them, such a foliation structure is not known, as I will describe in a bit. And then there's a type 2, famous example of which is the Haas code. And in this case, there are no string operators and the ground space degeneracy fluctuates with the system size. So to briefly describe the X-cube model, for X-cube model, you have a cubic lattice with qubits sitting on the edges, and these are the stabilizer terms. There is the one X stabilizer term and these 3 Z stabilizer terms, 2 of which are independent. And if you look at the logical operators in this case, you can choose a basis in which you have rigid string operators going along the lattice plane and the conjugate anti-commuting string operator going perpendicular to that plane. So that tells you that the number of string operators, since these are rigid, number of string operators or the number of encoded qubits is proportional to the system size. You have, in this model, you have one-dimensional particles called linons, which can move along the line, but if you try to move orthogonal to that line, you leave an excitation at the corner. But if you take a pair of these linons, you can move orthogonal to the dipole moment of the linon, which means you can move in a plane. Dipole moment of the pair, I mean. And similarly, you can have fractons, and these are the excitations. So the linons are the excitations of the Z stabilizer term, and the fractons are the excitation of the X stabilizer term in this case. And fractons are created at the ends of the sheet, and you create them in groups of 4, and they're completely immobile. That means you cannot move them by themselves. They need to move them. They need to move with other excitations. So if you take a fracton dipole, then it can again move orthogonal to the dipole moment. That means it can move in a plane. So this is an example of foliated type 1, which I mentioned, but I didn't say what it is. So foliation here means that it can be built from stacks of Toric code. Like you can take an X-cube model on this system size and put a 2D Toric code on top and do a local unitary, and you can grow the system size in that direction. So that's what it means by foliated. Fractal type 1 models have fractal logical operators, and such a foliation structure is not known. Okay, and now I want to briefly describe Haah's code, which is first one from the family of 18 cubic codes given by Haah. And these are the stabilizer terms for the Haah's code. So if you put this model on a closed manifold, then the product of all X stabilizers is 1 and product of all Z stabilizers is 1. So you get a minimum 2 qubits because of these relations. So in this case, in this model, if you apply a local operator on some qubits on some site, which has 2 qubits, then on the dual lattice, you create excitations at the vertices because the vertices are the stabilizers, and the excitation pattern looks something like this. You can apply multiple of these operators such that you spread these excitations apart, and you can keep moving them apart in this pattern such that you will apply a fractal operator, and these excitations will move apart in this fashion where they all move together, but each excitation is immobile by itself. So just for a picture, this is how a TQFT looks like, where you have all the excitations moving, possibly moving in any direction. And the type 1 fracton model looks like this, where you can only move along some rigid manifold, rigid directions. And the type 2 looks something like this, where you can only move in coordination with others. So with that, I want to talk about entanglement renormalization of these fractal models. So conventional notion of phases or equivalence classes of ground state wave functions leads to a notion of RG fixed points. such that these fixed points are representative of each phase. So each phase has a representative fixed point. And if you do renormalization, by which we mean you coarse grain the system, in the case of stabilizer, translation invariant stabilizer models, we mean that you enlarge the unit cell and basically integrate out any kind of short range correlations, then you will flow towards a fixed point, and that will be your representative of your phase. When we talk about entanglement renormalization, you can start with some model. Let's take this 1D representation, and then coarse grain. You basically enlarge the unit cell, and then remove any short range entanglement using a local unitary circuit. And then you can project out any disentangled degrees of freedom and repeat this process. And if it is, and sometimes you can get a bifurcating behavior of your model. So here we started with some model on this 1D lattice, and we split it into 2 models on the coarse grain lattice. So this is a bifurcating model. The conventional topological phases are believed to be fixed points of this entanglement renormalization process. Let me describe that a bit more. So conventional fixed points, if you apply this procedure of entanglement renormalization, so that fixed point gives you the fixed point back. But the bifurcating fixed points that we will discuss in this talk, if you apply this procedure on that fixed point, you get that fixed point Hamiltonian back, plus you get some other Hamiltonians, which we will find to be self-bifurcating. So because of the way I have defined this entanglement renormalization, it basically amounts to a local unitary equivalence. What coarse graining allows us to do, it allows us to have a bigger set of translation invariant local unitaries. So this is basically saying that this Hamiltonian on the original lattice is equivalent under a local unitary to these Hamiltonians on the coarse grain lattice. And this is basically, here by plus, I just mean, I will describe this more in a bit. So basically you get copies of these different models. So let's take some examples. So you can start with a set of trivial qubits. There's no interaction. And then coarse grain. And then if you put them on the coarse grain lattice, then you get copies of, basically you get 2 different copies of the set of trivial qubits on the coarse grain lattice. So in that sense, you started with a set of trivial qubits with lattice constant A, but then you get 2 sets of them on the coarse grain lattice. So in some sense, trivial qubits self-bifurcate trivially. And let's remember that for the next few slides. So if you do the entanglement renormalization of TQFT models, let's take the example of 2D Toric code. 2D Toric code, you can consider that it's on some system size, LXLY, and then you allow some trivial qubits to be added. And you can do a local unitary to grow the system size of this 2D Toric code. So in that sense, 2D Toric code is basically a fixed point, because you're allowed to add these 3 degrees of freedom to grow the system size. And this extra degrees of freedom that you added, we saw that they self-bifurcate. So this fact that you can grow the system size with just 1 copy of the original model corresponds to S equal to 1 in the SO3 framework of John McGreevy and Swingle. And the extra resource that we use is the self-bifurcating resource. So that has a higher S than S equal to 1. And we can also consider the example that we mentioned a while ago in this language. So the XQ model, you can grow by putting a stack of 2D Toric code on top, and you can grow the system size. If there's a whole stack, you can double the system size or increase it to any value. And the growing element in this case is the stack of Toric code. which self-bifurcates under entanglement renormalization. So
I have a question here.
yes.
I'm trying to understand this renormalization group. Seems like you have only one step. It's not like a flow that you look at like some fixed point. It's just you apply local unitary once.
So here I'm looking at the fixed point models. So these are bifurcating fixed point Hamiltonians. So I'm not really flowing to any particular fixed point. These themselves are bifurcating fixed points. So all I do is just coarse grain to have a bigger set of unitaries, like bigger set of allowed translation invariant unitaries. So when I coarse grain, I have that bigger set, and then I choose some unitaries from that set, and then I show that this model is equivalent to a bunch of models on a coarse grain lattice. So I would say that's why I mentioned that this is basically amounting to local unitary equivalence. That's all it is. But the coarse graining is done to allow for a bigger set of translation invariant local unitaries.
So I have a naive question. I'm already lost even on the simplest case where you say it bifurcates, something I should understand because you were explaining standard RG. So if you go back.
Yes.
Even further. Yeah, right here. I should have asked it here. I'm sorry I didn't.
No worries.
I don't understand where's the bifurcation. So I understand bottom line to the next line, coarse graining, but then what happens from middle line to the third line to the top line? Why is there a bifurcation? I would just read all those spins, you know.
So here I didn't do anything. I didn't apply any unitary. I just asked what happened to the model that we started with. So the model that we started with was a bunch of qubits with basically placed apart on a lattice with lattice constant A. And now on the coarse grain lattice, they are spaced apart as 2A. So if you take a single qubit, basically these set of qubits are now placed apart at lattice constant 2A, and then there's another set. So basically we didn't do anything. I think this will be more clear with the.
Okay, maybe this is some kind of a degenerate example, but I would have just said I now have the standard law would have been I now have another chain of qubits now further apart, you know, on the coarser lattice, but it's still one chain. I don't see a bifurcation unless I'm missing something.
Yeah.
So weird case.
Yeah, this is a very pathological.
Okay.
Example.
Yeah. So I mean, okay.
Yeah. I think I would try to clarify this more with better examples.
Okay.
The next few.
Thank you. Sorry.
Yeah. No worries.
I have a perhaps related question.
Yes.
When you perform this step, do you end up with a lattice with more points or with fewer points?
So I basically go to a coarse grain lattice. And so if you keep the system size same, so that means you have less number of degrees of freedom on the coarse grain lattice. So after you coarse grain, you basically have, if you keep the system size same, then you have less number of stabilizers, for example.
But I thought the number, if I understand correctly, you went from L to larger L.
Yes. So here, yes. So there is a slight. Here I'm going in the reverse direction. So okay. Yeah, this is probably something I should have been more careful about. So here I'm saying you can start with a L by L lattice and go to a 2L by 2L lattice. So which basically means you kept the lattice constant same, and you were able to add these degrees of freedom, extra degrees of freedom here, and increase the system size. So you can also go in the reverse direction where you start with this model and you increase the lattice constant and you disentangle some degrees of freedom. So
the lattice constant doesn't play a role here. Normally, when you perform this transformation, you go to a lattice which has fewer sites. You integrate out degrees of freedom, so you end up with fewer degrees of freedom. It looks to me like you start with L by L bits and you end up with 2L by 2L bits.
yes. So in some sense, I could also go in the reverse direction, where I have, let's say, a L by L like system size, and then I disentangle half of the degrees of freedom from that L by L lattice, where let's say the lattice constant is 1. And then when you disentangle these degrees of freedom, you get a higher lattice constant because you remove these extra degrees of freedom, and now you have a bigger lattice constant. So you can choose how you want to talk about it. You can talk about it in terms of lattice constant doubling from right to left, or you can talk about system size growing from left to right. But all we are doing is local unitary transformation with these extra degrees of freedom. And then we are talking about how you can increase the number of stabilizers in this case as you go from left to right. So you get a bigger toric code in that sense.
Can I ask a question about this unitary?
Yes.
Is the statement, are you making this change just on the ground state, or is this on the whole Hamiltonian? You're taking the whole Hamiltonian for the toric code with 2L by 2L and?
Yeah, these are the stabilizer generators. So yeah, I'm taking the Hamiltonian.
Okay. So you end up getting, after this unitary, Hamiltonian just for L by L, and then you have a whole other set of qubits not appearing in the Hamiltonian?
Yeah, so maybe I didn't hear the last part, but I can repeat. So I started with these trivial qubits over here, and I have a toric code. And now if I do a local unitary, I just put those, I basically included those qubits into the model itself. So, and I get a bigger, basically more stabilizers. So it's a 2L by 2L lattice now.
Okay, thanks.
Yeah.
When you do this, in either direction, you either do co-screening or in the other direction, do you have any requirement for the dimension of the local Hilbert space?
Sorry, I can't hear. The volume is pretty low.
I'm asking when you do this RG in either direction, do
Yeah.
you have requirement for the local Hilbert space dimension?
No, so yeah, so the requirement is I'm assuming it's so for all these models, I'm assuming it's a finite local dimension, and I will also assume that these are qubits or qubits, basically prime dimensional qubits, and I will focus only on those.
But do you allow the dimension to change after one step?
Oh, so at one side, yeah. So when I do code screening, you can have more number of qubits on one side, for example.
Sorry, I said, do you allow the local Hilbert space dimension to change after one step? For example, can you change a qubit to a 3-dimensional Hilbert space or 4-dimensional Hilbert space?
So I will talk about one example in which is the Haas code. So you can go from a model which has 2 qubits per site, And then you can, on the other side, like you start with a model with 2 qubits per side and do this local unitary transformation. And then on the other side, you get a bunch of models, and one of those models could have like 4 qubits per side, for example. So in that particular example, the local side dimension has increased. So that can happen.
Okay, thanks.
Yeah. So shall I proceed? Okay. Yeah, I'm trying to come to this notion that you can start with some Fracton model and then use an extra self-bifurcating model and grow that model by doing a local unitary in this fashion. So let me give an example of Haah's code, and things would be more clear when you look at this example. So you start with the Haah's code with some lattice constant A, do translation invariant local unitary after coarse graining. So this unitary is translation invariant with a coarser translation group. And then you get these models on a core with a coarser lattice constant, with a bigger lattice constant. So you get Haah's code back, and then you get some B model, which has a bigger on the coarse grained lattice, and a bunch of disentangled qubits. And then this extra model, which we call the B model, if you can do a further coarse graining and unitary transformation on this model, and then you find that you get copies of it of the same model. So basically it self-bifurcates. So Haah's code bifurcates into Haah's code and the B model, and then this B model self-bifurcates.
So what is H?
So H, by H I mean the Hamiltonian. So basically these are the stabilizer generators of your Haah's code.
So do you keep the size of the Hilbert space fixed or not? So imagine you have a finite lattice.
Yes.
And you have the Hamiltonian is a big matrix acting in that space.
Yes.
What do you change here? Do you change the size of the matrix, the size of the Hilbert space, or not?
I'm allowed to do only, so when I start with this model, I'm allowed to do only local unitaries on a translation, basically, which are translation invariant on the coarse grained lattice. So these new models, if you write them in a translation invariant form, the local Hilbert space dimension could be more than the local Hilbert space dimension of the model that you started with. So, but I'm not increasing the Hilbert space dimension when I'm applying this unitary. I'm basically just applying a local unitary, and I get a bunch of these models, and then there are these disentangled qubits. Maybe the confusion is if I go on the other side, if I can start with this model and add a bunch of disentangled qubits, and then go to the model on the left-hand side. And then I'm basically adding the extra degrees of freedom. So yeah. So this Haah's code bifurcates into Haah's code and the B model, and the B model self-bifurcates. So diagrammatically, I can represent it like this. We did this entanglement renormalization for many qubit code, and we found bifurcating behavior. So you start with this, for example, 1 qubit code, you get some B model, and you can get a stack of Toric codes, for example. And all of these extra models, they all self-bifurcate. And some of the qubit codes self-bifurcate themselves. Notice that we expect this kind of bifurcating behavior. It's consistent with the growth of number of encoded qubits with number of encoded qubits k with the system size. So if you multiply the system size by c, you basically multiply the number of encoded qubits by some constant. For bifurcating models, you're left with a constant correction. For self-bifurcating models, you have no constant correction as you change the system size. So Fracton models generally bifurcate under entanglement renormalization. So you start with some model and do this unitary, and then you get a bunch of models. So you get the original model and some self-bifurcating models, which under entanglement RG show this behavior. So self-bifurcating models can be considered as resources for growing the system. So all I want you to take from all this explanation is that I start with a Hamiltonian, I start with a bunch of stabilizer generators and apply a local unitary, which is translation invariant on a coarse grained lattice. And then I get some decoupled models out. When we did this entanglement renormalization, we saw that the models that we get after doing the local unitary are related to the set of mobilities of particles in the original model. For example, Qubit code 11, which is one of the models, has particles of mobilities 0, 1, and 2, which means it has fractons, linons, and planons. And when we did the entanglement renormalization of this, so you basically applied some local unitary on a coarse grained level, and you found that you get a copy of the original model, Qubit code 11, and some B model which self-bifurcates, and a stack of Toric code. So the stack of Toric corresponds to having these planons, and this B model was a linon model, which means that the lowest mobility in that model was one-dimensional. And that corresponds to having this linon. And the fracton basically corresponds to having the original copy of Qubit code 11 back. So this led to some conjectures about the structure of these stabilizer models. And now I'm going to talk about those structure theorems, basically. So, what we found is, and now I have proven some of these conjectures. So if you have a 3-dimensional bosonic particle, then you can do a local unitary to extract a 3D toric code from the stabilizer. If you have a fermionic particle, which is mobile in all 3 dimensions, then you can extract a 3D fermionic toric code. And if you have a 2-dimensional particle, then you can extract a 2D toric code. And similarly, and there's a corollary of this 2-dimensional case. If you have a 3D stabilizer model which has only planons, then that is equivalent to stacks of toric code, stack of toric code. And similarly, if you have a 1-dimensional particle, which is a linon, then we cannot find a particular model that is extracted after entanglement renormalization, but we can say that you will extract a linon or a fracton model out just by definition. And similarly, if you have a fracton in the original model, then you will extract a fracton model out. And these two just follow by definition. We can't really say which particular model will be extracted. And I will explain that why when I discuss the proof of one of these. So in this talk, I want to just show the proof of this one and the proof of the remaining. The proofs of the remaining are similar, or they are just more cumbersome to show. So for this bosonic 3D particle case, the proof uses bosonic statistics and 3-dimensional mobility of excitation to restrict the form of corresponding stabilizer. So this will help us to basically show that one of the stabilizers looks like this. And then we will use the topological order condition for translation invariant stabilizer models to find the generators of terms that commute with this first stabilizer, and also maintain topological order and translation invariance. And then we will get this model out. So that's the 3D toric code. So for that, I want to use this polynomial representation for stabilizer models. So there's a concept of a stabilizer map, which is you can imagine that as a 2q times t, where q is the number of qubits on on a single site, and T is the number of stabilizer generators. And this is a 2Q times T matrix, which basically maps qubit position labels to polystabilizer generators. Let me explain this through an example of Bifurcate model. So this is how these circles are different qubits. So there's only a single qubit per site, and these are the stabilizer generators. So there's a single stabilizer generator, and then the remaining are just translates of that one. So, and this is how we label the positions of qubits in the polynomial description. So you can just call this one as 1, and the next one is x in the x direction and x square, and similarly in the y and other directions. So, and you have this as your stabilizer generator. So the first, since it's a 2Q times T map, so T is just 1 because there's only one stabilizer generator, and 2Q is the first Q rows are for X poly operator positions, and the next Q rows are for the Z poly operator positions. So if you look at the stabilizer generators, the Z poly operator is at positions X and Y. So you put X plus Y in the second row, and the X poly operator is at positions 1 and XY. So you put 1 plus XY in the first row. And that's the stabilizer map for Bifurcate model. So, and if you want to write down a stabilizer at a position X, so this position 1 is for this stabilizer is at position 1. You can similarly label the stabilizer positions, and this is a position X stabilizer. So you can write down that stabilizer by just multiplying sigma to X. So that gives you the stabilizer generator at this position, and so on. And then another concept which is important is the excitation map. And it's a T times 2Q map from local poly operators to positions of excited stabilizers. Let's say you apply some local operator and you want to see which stabilizers are excited. So for this, we want to label the different stabilizers. So I've labeled the stabilizer generators like here, 1x, y, and xy. And now I apply some local operator at this qubit position. And this local operator is, let's say, a Z operator at this qubit. So Z here is written as 0 and xy because xy is the position of the Z operator, and there is no x action. So basically, this is the representation of Z operator. And you can define this excitation map in this manner. It's sigma dagger times an antisymmetric matrix. And sigma is what I defined before, which is a stabilizer map. And dagger basically just takes the antipodes of these translation variables, x, y, and conjugate, and also do the transpose. So for example, yeah, that's not important. So I did the sigma dagger times lambda, and then I got this excitation map. And when you add this excitation map on this Z operator, you get the positions of these excited stabilizers. So, and this 1 plus xy is called the excitation pattern for this local operator. And we will also call these local operators as movers when they create a pair of excitations, because you can then take a sequence of these movers and basically create a string operator to move these excitations apart. So in this case, this mover, which is 0, 0, xy, it basically moves the excitations apart in this direction if you apply a sequence of them. And the next thing which is important for the proof is to write the topological order condition in terms of these excitation and stabilizer maps. So the topological order condition is given by this, which says that the kernel of this excitation map is the image of the stabilizer map, which basically is saying that any local operator that does not create any excitations belongs to the stabilizer group, or no local operator can distinguish between the ground states of the topological stabilizer model. Okay, besides this, another ingredient that will go into the proof is the self-statistics of this bosonic excitation, so which is defined as follows. So you can take a process in which you have the same excitation type, two of them, and you can move this excitation in this manner, and then move the one at the other end, and basically exchange the excitations of the same type. And this whole process is represented by this operator, and it acts as identity on your stabilizer generators or on your ground state, for example, up to a phase. And this phase, theta, is telling you the exchange statistics of or the self statistics of this excitation. And I can take these operators as long string operators, which the operators which I showed before, as string operators that basically take this excitation from -infinity to 0, or like from far away to the origin, and basically move them to exchange these excitations. And then you can express this phase theta in terms of our polynomial notation in this manner, where an and bn are these operators represented in the polynomial notation. And the commutator, and the commutator here is 0 if and only if the coefficient of 1 in an dagger lambda bn is 0. That's an extra detail which is not required for at the moment. So an is, you can imagine this long operator, which basically takes the excitation from here to here, is many movers, is a sequence of movers. And let's say the mover is px of e, where this excitation is created in pairs by px. But then if you apply a sequence of that mover, then you are taking an excitation from -infinity to 0 if you take the limit n going to infinity. And similarly, you have a representation for these other string operators. And when I said mover, I basically meant that if you act this excitation map on this local operator, you create a pair of excitations. In this case, you create a pair, one of the excitations at 1 and the other one at x. And this is the charge. This is the excitation, which we label by E. So for bosonic particle, this phase theta is 0. And I won't show in detail, but after sufficient coarse graining, this being 0 basically amounts to the fact that px dagger lambda py is 0. So lambda here is the antisymmetric matrix that I mentioned when I defined the excitation map, this matrix. So so these different movers and their translates commute, and that is captured in these expressions, that these movers and their translates are commuting, and that's because of this condition that theta has to be 0. So after sufficient coarse graining, we get this. And this is a generalization of a lemma of a paper by Haah for 2D particles. It's a straightforward generalization. So a 3D particle has movers, basically creation operators, which create excitations in pairs. So you act the excitation map on these movers, you get a pair of excitations. And this charge E shouldn't belong to the image of the excitation map, otherwise it's trivial. And we are assuming this is a topologically non-trivial charge, so we impose this condition. And after doing sufficient coarse graining and C0 and C phase operations, you can choose these movers to have such a form where you have in the first Q rows, you have just 1 in one of the entries and rest all are 0. and yeah, and same for py and pz. And two of the entries in the remaining queue from q plus 1 to 2q are non-zero for each of these movers. And you can do a further C phase operation such that they look like this. These px, py, pz. So we went from these ax, bx, ay, by, az, bz. So these are some non-zero polynomials. We just don't know what they are. After sufficient coarse graining, you can make them simple monomials and then do a C phase operation to reduce them to this form, to reduce these movers to this form. And then if you impose this condition of the commutation of movers and the translates, these terms are all zero. So basically you get this form for the movers where they're all just unit vectors. So these px, py, pz are all unit vectors. And now you can choose a basis of stabilizer generators such that the 3D bosonic particle, that charge is represented as a unit vector in this polynomial representation. And the unit vector, you can choose that it's just the one is at the top. This is just a basis to us. And then if you impose this condition that this excitation map acting on a particular mover is like, let's say px is x minus 1 times the charge, then from using the simplified form of the movers, as we found here, we can show that this gives a particular form for the excitation map where the first three entries are x minus 1, y minus 1, z minus 1, and all these remaining in that column are 0. So this is a column, this is a t length column, and this is a 0 is a t minus 1 column vector.
Hey, Arpit,
yes.
Sorry for the interruption. You should wrap up probably soon. Yeah, I mean now.
Yeah, so I'm almost done. I just want to, yeah, just give me 3 minutes.
Okay.
Yeah, so this is what we get, and these are some entries which we don't know. And just because this excitation cannot belong to the image of the excitation map, we can show that every other entry in this first row belongs to a linear combination of these excitation patterns. And so you can make all of them 0 by applying C0 and C phase operations. So you accept these three. Okay, and now we want to use the topological order condition. We can show that these vectors belong to the kernel of the excitation map, which is same as the image of this sigma. And just because of this condition, this is just following from this form of the excitation map. We can show that you get these extra rows in your excitation map. And so you're left with this form. And then by just using the commutation of different stabilizer generators, you can make everything else 0. And what you're left with is this stuff in the red, which is decoupled out of your original model. And this is the 3D Toric code. So we showed that you can extract 3D Toric code for bosonic 3D particle. Similarly, you can show that for fermionic particle, you get fermionic Toric code. And for a 2D particle, you can get a 2D Toric code. So what helped in getting these, improving these theorems is that there was a fixed form of these excitation patterns. Like for 2D particle, it was like 1 plus x, 1 plus y. For 3D particle, it's 1 plus x, 1 plus y, 1 plus z. So these fixed forms of the excitation patterns provided sufficient conditions to extract the Toric codes. For linear fractons, excitation patterns have many possibilities. So a particular model is not extracted, but you can just work out which model will be extracted depending on the excitation patterns. Yeah, and with this slide, I want to just leave it.
Thank you very much, Arpit. Okay, I think we had several questions during the talk. So let's thank the speaker again, and let's move on to the next talk. Thank you, Arpit.
Okay, thank you.
Yeah.
Islam?
Yes.